Welcome back, everyone. My name is Susanna Smith, and this is going to be the last PowerPoint presentation for the class Business Research Methodology and Quantitative Statistics. The topic of this presentation is going to be on conducting a simple regression and reviewing the literature. Okay, everyone, we have a very straightforward agenda for this PowerPoint presentation. First, I wanted to go into talking about different common terms for simple linear regression. Then I will discuss three different types of hypothesis tests. The first regression test will involve debt and income. The second test will involve savings and income. And the third test will involve stocks and savings. I would then go into detail about three different articles that I found very helpful for me for this class. They will include annotated bibliographies, and I will summarize the content. Then I will go into main takeaways for this PowerPoint presentation, and I will conclude with questions and answers. All right, so here are some common terms associated with simple linear regression. Simple linear regression is a statistical method that allows us to summarize and study relationships between two continuous variables. The model for simple linear regression is y equals beta 0, or the intercept, plus beta 1 multiplies the x, which is also known as the slope of x, or the coefficient of x. The main objectives of simple linear regression is to establish if there is a relationship between two variables. More specifically, is there a statistically significant relationship? One variable, denoted as x, is regarded as the predictor or the independent variable. The other variable, denoted as y, is regarded as the response, outcome, or dependent variable. The regression model is an equation that describes how y is related to x. In this situation, the simple linear regression has a null hypothesis, which is beta equals 0. The alternative hypothesis is beta does not equal 0. There are different types of relationships that can be found within a simple linear regression. Those are deterministic, functional, and statistical. Some examples of some variables that are commonly utilized for testing purposes can be things such as height and weight. As height increases, you would expect weight to increase. Alcohol consumption and blood alcohol content. As the alcohol consumption increases, you would expect one's blood alcohol content to increase. Lung capacity in smoking. The amount of smoking increases, the amount of lung function would be impacted. And driving and gas mileage. So here is our first hypothesis test that we conducted utilizing the simple linear regression model. The sample data set that we used for this test was debt and income. After performing the test, it was determined no significant result was found. So how did we come to this conclusion? We created the null hypothesis, and in this instance, we utilized the model. The regression coefficient beta is 0. The alternative hypothesis is then the regression coefficient beta is non-zero. A simple linear regression was conducted to determine whether debt could be predicted from income. No significant regression was found utilizing the PSPP tool. So let's take a moment to break down the data we discovered from the tool. So we have income right here, which is our regressor. Beta, which is a symbol right here. The number for beta is negative 0.05. R squared is 0.00. And this p-value here is 0.535. Now typically, if the p-value is less than alpha, we would reject the null hypothesis. In this instance, because it is the opposite of that, we fail to reject the null hypothesis. And then we determine that there is no significant result found after conducting the test. So here we have the second hypothesis test that we conducted using the simple linear regression technique. The sample data set that we used is savings and income. After performing the simple linear regression, a significant result was found. So let's break down the hypothesis tests. The null hypothesis is the regression coefficient beta is 0. The alternative hypothesis is the regression coefficient beta is non-zero. A simple linear regression was conducted to determine whether savings could be predicted from income. A statistically significant regression emerged. Beta equals 0.91, R squared equals 0.82, and the p-value equals 0.00. Thus, the test rejected the null hypothesis, and savings equals 0.91 times income minus 203.47. This means that savings is predicted to decrease as income increases. Further, the 95% confidence interval 0.09 and 0.11 does not contain 0. Hence, this lends further support to the prediction. So once again, let's talk about some of the numbers that we retrieved from the PSPP tool. Here we go, we have income again, which is the regressor. This symbol right here is beta. So beta is 0.91. R squared equals 0.82. And this is the p-value here. So when you compare the p-value to alpha, when it's less than 0.05, that means you are to reject the null hypothesis. And then in this case, that's what occurred, and we determined a significant result was found. So here is our third and final hypothesis test we will be performing using simple linear regression. The data sample for this is stocks and savings. After conducting the regression test using PSPP, a significant result was found. So how did we come to this conclusion? The null hypothesis is the regression coefficient, or beta, is 0. The alternative hypothesis is the regression coefficient beta is non-zero. A simple linear regression was conducted to determine whether stocks could be predicted from savings. A statistically significant regression emerged. Beta equals 0.28, R squared equals 0.07, and the p-value is 0.00. Thus, the test rejected the null hypothesis, and stocks equals 0.28 times savings plus 1006.73. What this means is that savings is predicted to decrease as income increases. Further, the 95% confidence interval 0.07 and 0.25 does not contain 0, hence lending support to the prediction. Let's take a second to once again highlight the different components of this test. Savings right here is the regressor. The beta value is right here, 0.28. R squared, 0.07. And once again, here you go, you see the p-value, it's less than alpha. And this results in us rejecting the null hypothesis, coming to the conclusion that a significant result was found. So the first article I wanted to talk about is called Logic of Hypothesis Testing by David M. Lane. This was a very good article for me because it helped break down hypothesis testing in a really simplistic manner. So Mr. Lane goes into detail and starts talking about the concept of hypothesis testing, and he provided a really good definition. It is a statistical technique for testing whether chance is a conceivable explanation of an experimental finding. From there, it was helped establish for me that hypothesis tests are usually done by the creation of a null and alternative hypothesis. The null hypothesis it assumes there is an apparent effect due to chance. The alternative is always the opposing view of this, and it is the reverse of the null hypothesis. The p-value, which is the probability of obtaining a statistic, is different or more different than the parameter specified in the null hypothesis. The null hypothesis is rejected if the probability value is less than 0.05. That was what the set standard we utilized throughout the course of this class. When a probability value is below the alpha level, the effect is statistically significant and the null hypothesis is rejected. So, if the p-value turns out to be greater than alpha, we fail to reject the null hypothesis, and what this means is that we assume there is not an identifiable consequential relationship between the two variables. So let's break it down a little bit more than that. Let's talk about it in a really simplistic manner. The process is like this. As a researcher, you would formulate the null and alternative hypothesis. You would identify a test statistic to assess the truth of the null. You would then compute the p-value, and then you would compare the p-value to an acceptable significance of alpha. A hypothesis test is also known as a test of significance, and it is a standard procedure for testing a claim about a population. So, in simplistic terms, we test the null hypothesis directly, and we either reject the null or we fail to reject the null. So let's break it down into really a simple example here. So we as consumers sometimes like to order takeout. So for example, suppose a restaurant claims their delivery times are about 45 minutes or less. But in reality, you and I both know that's probably longer than 45 minutes. You conduct a hypothesis test because you believe the null hypothesis is of being less than 45 minutes is incorrect. The alternative hypothesis would be that the mean time is greater than 45 minutes. You do a random sample of the data, and the p-value turns out to be 0.02, when the set standard is 0.05. So from that conclusion, what does that mean? You would reject the null, and you would determine that yes, chances are the 45-minute or less time frame is actually incorrect, and it turns out the restaurant needs some delivery drivers that need to drive a little bit quicker because of what people ordered. The second article I wanted to talk about is something written by John McDonald, and it was in regards to the topic of chi-square test of independence. So this article is really important for me because the chi-square test of independence was pretty intimidating for me at first. When I first began reading the assignments, I was somewhat terrified. I didn't know what the test was. I couldn't really computate it. I couldn't really understand it, and it was a little bit hard for me to understand how to apply it using PSPP. But this article helped break it down and provided me some good information that I wanted to share with everybody in hopes that maybe it'll kind of alleviate some other person's stress later on once they reach this assignment. So the chi-square test of independence, used for when there are two nominal variables or categorical variables. It is determined whether the proportions are different from one value to another. Nominal variables are used. It classifies observations into discrete categories. The test utilizes a contingency table to analyze the data. And when you're doing the PSPP tool and test, it'll help break it down into what it means. A contingency table also is referred to as cross-tabulation or cross-tab or a two-way table. When you utilize the PSPP tool, there are different labels for different tests that are performed. So it'll help for you to become familiar with what contingency tables are also called in these tools. It is basically an arrangement of data classified according to two categorical variables. Now, I wanted to really reference during this time frame when it's categorical variables, that does not mean that they're quantitative, they're qualitative in nature. The chi-square test of independence only assesses associations between categorical variables and cannot provide an inference about causation. So it really kind of more or less touches upon some generalized perspectives. It does not go into detail in terms of the strength of the relationship. So data requirements. Well, in order for it to be performed, you need to have two categorical variables, two or more categories such as groups for each of the variables, independent observations, and a pretty decent large sample size, or you're really going to have information that becomes skewed. So let's talk about different variables that you can utilize. Something, we'll just say gender, for example, is a good value. Genotypes, because a lot of times this type of testing is done in a lot of scientific settings. Talking about different conditions and physical health conditions. And any other observations, maybe you could talk about people's height and weight. You can talk about some politics, different politics, whether or not someone is a Republican, Democrat, so on and so forth. So now let's demonstrate an example of a chi-square test of independence. Let's say we want to determine whether gender is independent of becoming a smoker. We have the sample size of 2,792 men who reported they smoked, 3,591 women who reported they smoked, 1,486 men reported they didn't smoke. 2,131 women reported they did not smoke. So the solution is as follows. The null hypothesis would be, is gender independent of smoking? The alternative is gender is dependent of smoking. So you would have the table formulated, the contingency table, and it would be computed under assumptions that rows and columns are in fact independent. The computation equates to observed numbers minus expected numbers equals the difference. So what I learned from the article is the smaller the difference, the better the fit in favor of independence between gender and smoking tendencies. The first step to computing the totals is to reach the grand total. So let's break that down a little bit further. The total number of smokers is 6,386. The total of non-smokers would be 3,617. The total of men for both smoking and non-smokers is 4,278. The total for women would be 5,722. The grand total for both men and women respondents would be 10,000 at that point. Through the use of an automated tool, The test reviewed the goodness fit value of 6.66. This in turn would exceed the chi-square value of 3.84. In this instance, the p-value would be less than 0.05, which means we rejected the null hypothesis. Now, you would then want to, in this instance, proceed with the Kramer's V assessment to determine the strengths of the relationships of the variables. I do want to mention that these are just an example of how the chi-square test of independence can be conducted. And this just shows that if you pulled a different sample, you could also get different results. It depends. The next time you pull the sample group, maybe there would be less women who determined that they reported they smoked and more men that reported they smoked. It all just depends on how the sample size responded to you in that moment. There is no exact science to always acquiring the same results over and over again when you perform these types of hypothesis tests. So this is the final article I wanted to talk about that was very helpful for me throughout the course of this class, and it involves the topic of Likert scaling, and it was written by William Trocum. Now, what exactly are Likert scales? They are a common rating format that you see within surveys. Why is it important? Well, these types of scales are seen often in hypothesis tests. When we rely on hypothesis tests, a lot of times we rely on data that is pulled from resources out in the field. People that respond to surveys, we retrieve that data, and that's how we perform hypothesis tests. It is a desirable way to learn whether the construct or concept is a single-dimensional or multi-dimensional one. It is a process that is a part of exploratory research. Respondents rank quality from high to low or best to worst using 5 or 7 levels. Measurement systems include nominal data, and this is types of measurements that represent categories and they don't have numerical representation. Ordinal data, data in which are ordering or ranking, but there is no measuring of distance associated with it. Interval data, which is generally integer data in which ordering and distance measuring is possible. And ratio data, data in which meaningful ordering or distance decimals between variables are possible. Common Likert scales, well, you can have a 5 or 7-point ordinal scale used for respondents. And it is used to rate the degree of which they agree or disagree with a statement. So let's show the Likert scale in action. So let's say you want to measure consumer satisfaction. You're a company and you're really interested in seeing what the population and consumers think about how your company is performing. So you gather all these people together and you develop some questions that you want to present over to consumers. Researchers then could ask consumers a series of 5 questions using unipolar statements. So what do I mean by unipolar statements? Well, here's a question for you. How satisfied were you with your in-store experience? From there, you would have a series of different categories of satisfaction levels that the consumer can choose to pick. So they can say, yes, they were extremely satisfied. Yeah, they were very satisfied. Or the middle of the road, moderately satisfied, slightly satisfied, and not very satisfied at all. Let's show it again. Okay, so let's say you asked a consumer about what their thoughts about product offerings within the store. You approach them, you ask them this question, and the 5-point Likert scale would be presented like this. They have the option to present extremely satisfied, picking that as an option, very satisfied, moderately satisfied, slightly satisfied, and not satisfied. So what is the purpose of the Likert scaling? Well, it is a really simplistic way to gather and analyze data so that you could present it in a research findings without really going overboard and gathering information that could be really skewing the results. So the purpose of this article really demonstrated how there are ways towards certain types of questionnaires so that they are very simplistic and easy to follow, and how researchers can actually acquire the best types of results that can be articulated and incorporated into a research finding so that it could be presented. And it's very important when you have a company, because they want to be able to look at information and really take it and look at it and improve the way that they do and run the business so that things can improve in the future. So there are several takeaways that I wanted to point out from this PowerPoint presentation. So linear regression, it can be an intimidating process, especially if you go ahead and try to do it by hand. But ultimately, in this day and age, there are very many different software tools available out there that can really help improve the automation of trying to analyze different data through conducting linear regression. So we performed 3 different tests, and there were 2 significant results that were found: savings and income, stocks and savings. The one non-significant result that was found involved debt and income. So linear regression suggests that the relationship between the dependent and independent variable can be expressed in a straight line. So with this, there are certain different components that are important to remember when you're doing a linear regression. There's beta, R-squared, and the p-value. Linear regression models are not perfect. What this means is that a lot of these things depend on the data samples that you choose to analyze. And then on top of that, there is a certain level of approximation that takes place. Approximation leads to errors. Some errors can be reduced, but in some situations, errors are inherent in nature. These errors can't be eliminated, and these things are called irreducible errors. So let's talk about an example of a regression model that we can talk about and break down. So my father, who has just retired, he feels like he wants to buy himself a car. So he's very good on analyzing. He was a former budget analyst, so he wanted to go in and estimate and predict the car price that he would have to pay, because I feel like he deserves a Mercedes. So he has a friend who works at a car dealership, and he asks for prices of various cars along with characteristics of the cars. So here he is looking at different variables, and he has decided upon the following hypothesis. The null hypothesis he has created is that there is no relationship between price and engine size of a car. The alternative hypothesis is that there is a relationship between the price and engine size. So what does this mean? In his eyes, it implies there is some type of relationship between price and engine size, and the p-value is a probability value that indicates the chance of seeing the given t statistic on the assumption that null hypothesis is true. If the p-value is small, less than 0.05, it implies that the probability that this is by chance and there is no relationship is very low. In this case, the p-value is small and means the relationship between price and engine is not by chance. So what does that mean? Well, you should reject the null and assume that there is a correlation and find a significant finding and assume, yes, the larger the engine size, well, the more money you're most likely going to pay. So what does this mean when all is said and done regarding statistics? Statistics are a set of mathematical equations that we use to analyze things. We do it on a regular basis. We do it for all sorts of reasons. We do it without any even scientific motive. Sometimes we do it just to articulate different information so that we can make certain decisions in life. What does this mean? Well, it keeps us informed about stuff. It helps us really understand how things are occurring within the world. So in closing, I just wanted to say that this has been a very, very interesting class, and it really has allowed for me to understand that statistics is a very big component, and there were times that I was actually using it and I didn't even know. Thank you everyone for watching my PowerPoint presentation. I hope you enjoyed it, and good luck on your future journeys. Thank you and have a good one.